For term 2 2021, we'll be taking Sola2051. In this course, students were given the opportunity to design and build a boost converter to charge their mobile phones by using a mini solar panel. Split into groups to undergo this mission, one group was known as Team H. This is their story. This team consisted of Zach, Albert, and Ibrahim. At the beginning, we needed to characterize each solar cell for their key performance parameters. By using a bunch of these formulas that we've learned through other courses, we were able to calculate the key performance parameters. With these 6 found, the last 3 needed to be manually adjusted to best align our data with our measured IV curve. With our almost perfect IV curve, we can now extrapolate these values. Given them, we were able to model our solar panels in LT-SPICE for temperature simulations. We modeled the panels at 15, 25, 30 and 45 degrees to find out that the hotter the panel, the lower the open circuit voltage. So, in order to get the best out of our panels, we need them to be as cool as possible.
To ensure that the panel is maintained at cool temperatures, cooling mechanisms such as openings at the rear of the panel for airflow access and the use of a heatsink for effective heat transfer were deployed. The use of the heatsink involved the heat located at the rear of the solar panel to be transferred to the heatsink via conduction, which is then transferred to the surrounding environment by convection and radiation at the fins. Since aluminium has a high thermal conductivity, strips of aluminium foil initially used for insulating foods were repurposed. Before analysis of the boost circuit was conducted, the oscillator circuit, which has the function of producing the PWM signal for switching, was evaluated, where it was found that as the resistor values, especially the feedback resistor of the oscillator and the size of the capacitor is decreased, the frequency of the PWM is increased. Before simulating an LT-SPICE, the non-ideal internal resistances of the inductors were determined and added in the LT-SPICE. As seen, the 104C inductor was preferred as it had the smallest internal resistance and thus the smallest power dissipation. The task of optimizing the boost circuit was conducted through parametric analysis in LT-SPICE. By extracting the maximum output voltage for all possible boost circuit configurations, the optimum circuit could be identified. The boost converter which yielded the best performance was that of the 100 microhenry inductor and the 1 nanofarad capacitor in the oscillator circuit.
As per project guidelines, the LabVIEW has a PID that can adjust the output power to the required value by varying the duty cycle both manually and automatically. New data values are uploaded to the cloud every 15 seconds, with the exception of insolation, which is uploaded every 3 minutes. To ensure that the insolation uploaded is near short circuit, a separate PID is used to bring the input voltage down to 2 volts, which is sufficiently close to short circuit. This PID activates 10 seconds before every 3-minute mark so that the input voltage has time to reach and stabilize at 2 volts. The insolation value calculated at the 3-minute mark is then uploaded.
The final testing wasn't too lucky for our team. Albert's Arduino refused to connect and Zach's circuit components were very faulty. My solar mount wasn't optimized. And after an hour and a half of testing, my circuit had started overheating and my efficiency had plummeted. Even though I was getting input power values of 800 milliwatts, my output power was nearly half of that. We could have spotted some of these issues during testing, but due to many factors such as there have been only 2 weekly online labs and with circuit issues and LabVIEW timing bugs, we simply didn't have enough time to test. Even the PID constants used for the final testing were rough estimates, and we had to manually control the duty cycle many times during the actual test.
The group passed through multiple stages of discovering errors which ranged from misconnections, damaged op-amps, diodes connected with the incorrect polarity, and potential breadboard issues. Since a large portion of time and effort was spent troubleshooting the circuits, smaller tasks such as adding mean functions to reduce noise and data and setting more suitable PID constants through trial and error was left incomplete. Despite all this, overall and throughout this course we learned about new electrical circuits and their components, the importance of communication and teamwork skills, the use of the LabVIEW program and its ability to work in conjunction with the Arduino Uno, which enhanced our programming skills, and the importance of being able to adapt to unexpected challenges and problems, all of which are beneficial and crucial to any upcoming and studying engineer.